Now we move into diodes and applications. We're going to look at a quick introduction to semiconductors, and then we're going to get into the diode characteristics, rectifiers, power supplies, and then toward the end hit the special purpose diodes. And if there's anything of interest in the troubleshooting, we'll take a look at that as well. So we can see that the terms that we're interested in: silicon hole intrinsic semiconductor. Hopefully you had all of this in your DC class. I believe that this information is presented to you at that time. So take a look at the terms here. Make sure that you understand what each of these terms are in fact telling you. So we're going to take a look at an introduction to semiconductors and look at, just real quick, the basic structure of an atom as it applies to a semiconductor. So you've probably already seen that we focus on two types of elements here: the silicon and the germanium. And you can see from the diagram here the difference between the valence electrons and outer electrons in the outer shells for silicon and that of germanium. Of course, what goes on the outer shells, the valence shells, is where we get the activity or the action of the semiconductor, when we're able to strip off those valence electrons and use them to move electrons and create electric current through a semiconductor. But because it's not a full conductor, unlike a piece of copper, they have to be coaxed. They have to be teased into moving off of that outer valence electron and jump from another. So some things that have to happen then is the material typically has to be doped so that you have other elements in there to help the current to flow. Atomic bonding: when certain atoms combine to form a solid material, they arrange themselves in a fixed pattern called a crystal. The atoms within the silicon crystal structure then are held together by covalent bonds, which are created by sharing the valence electrons with each atom. So we can see from the picture here what's going on as the atoms then link and unite in those outer rings, or those outer valence shells. So the intrinsic crystal then, in this case, has no impurities. You notice all we're talking about here is silicon and sharing valence electrons in silicon. So looking at conduction, electrons and holes, an energy band diagram then will show for a silicon crystal with an unexcited, no energy, external energy such as heat being introduced to get the activity. So in this case, they say that the condition occurs only at a temperature of absolute zero, and this is in Kelvin. Notice it doesn't say degrees Kelvin, it's 0 Kelvin. An intrinsic pure silicon crystal then at room temperature then has sufficient heat, thermal heat energy, for some valence electrons to jump the gap from valence band to valence band into the conduction band, or the conduction mode. And at that point they become free electrons. So if we scoot down here to the diagrams, we can see then what's happening with these energy bands. The energy band diagram for a pure silicon crystal then with unexcited atoms, then no electrons in the conduction band. So you can see here from first band or shell, second band shell, valence band, there's no excitation. There's nothing forcing these valence electrons to move through the energy gap and into the conduction band. So the creation of electron hole pairs then in a silicon crystal, then here moving valence to conduction, the electrons in the conduction band then become free electrons. So you can see here in the diagram they've put a little heat on here to excite the valence electrons, and then they will start sharing from valence band to valence band, something that we call the conduction band. So this is your energy diagram and your bonding diagram. Electron hole pairs then in a silicon crystal, free electrons are being generated continuously while some recombine with holes. So now we look at a lattice here, an arrangement then of many electrons paired together, and you can see they've applied heat energy to the element here, to the silicon. And so a generation then of an electron hole pair, the hole then becomes a vacancy. So when a electron jumps to the ring of a neighboring silicon valence band, we create a gap here, and that gap is the hole. So it's that movement of electrons or holes, depending on how you want to think about it, that occur that really is the flow of electrons in what we call current. So you can see here in every case here, we've created holes as electrons are jumping off with the application of the heat. Electron and hole current then, when a voltage is applied across a piece of silicon, the thermally generated free electrons in the conduction band, which are free to move randomly in the crystal structure, now easily attract toward the positive end. So whenever a hole is created, an electron jumps off to try to fill it. This movement of free electrons then is one type of current in a semiconductive material called electron current. Another type of current then occurs at the valence level, where the holes created by the electrons exist. Electrons remaining in the valence band are still attached to their atoms and are not free to move randomly in the crystal structure. However, the valence electron can move into a nearby hole with little change in its energy level, thus leaving another hole where it came from. The hole has effectively, although not physically, moved from one place to another in the crystal structure. So that becomes a hole current. So we can see here then on the hole current diagram here what's happening. We can see that electrons are jumping off to fill a hole. So you've got one electron jumping to this hole. You've got one electron jumping to this hole as we create these links and holes and current movement across the structure. So if we compare then semiconductors to conductors and insulators, in an intrinsic semiconductor, that's a pure semiconductor, we've added no doping, there are relatively few free electrons. So semiconductors are not very useful as intrinsic states. Pure semiconductor materials are neither insulators nor are they good conductors, because the current in a material depends directly on the number of free electrons. So if we look at a comparison then of the energy bands for insulators, semiconductors, and conductors, we can see the essential differences among them regarding conduction. The energy gap for an insulator is so wide that hardly any electrons acquire through the energy to jump into the conduction band. The valence band and the conduction band in a conductor, like in copper, overlap so that there's always many conduction electrons, even without the application of an external energy. A semiconductor then has an energy gap that is narrower than an insulator, so it's in between that of a conductor and an insulator. So we can see that here when we look at an insulator, a semiconductor, and a conductor. So with the semiconductor, what we have to do is we have to tease it or excite it so that we get the flow of electrons. P and N type material for semiconductors. Semiconductor materials do not conduct well and are of little value in their intrinsic state. This is because the limited number of free electrons in the conduction band and holes in the valence band. Intrinsic silicon must be modified by increasing the free electrons and holes to increase its conductivity and make it useful in electronic devices. So in doing that, that's how we control the flow of electrons. For those of you that ask questions about dependent versus independent sources, semiconductors are what controls the dependent sources. Independent sources are able to operate on their own. Dependent sources require a semiconductor to get the control and flow of electrons. This is done by adding impurities to the intrinsic material, as we'll learn in this section. Two types of extrinsic or impure semiconductor materials are the N and the P type. And they are the building blocks for all types of electronic devices. So how do we do this? As I said, we do something called doping. The conductivities of silicon can be drastically increased and controlled by the addition of impurities to the intrinsic pure semiconductor material. The process called doping then increases the number of current carriers, electrons and holes. The two categories of the impurities are N-type and P-type. The N-type semiconductor then increases the number of conduction band electrons in intrinsic silicon. What we call a pentavalent impurity atom is added. These are atoms with 5 valence electrons, hence the name penta. And we use such material or elements such as arsenic, phosphorus, and antimony, and are known as donor atoms because they provide an extra electron to the electron's crystal structure, and we'll see that in the diagram. For the P semiconductor, to increase the number of holes in intrinsic silicon, a trivalent impurity atom is added. So in this case, we want to add 3 valence electrons, so we might use something called something like aluminum, boron, and gallium that have a known acceptor atom because they leave a hole in the semiconductor's crystal structure. So if we look at the diagrams here, then we can see the pentavalent structure and the trivalent impurity atom when we add a doping atom into the mix. So as illustrated above, each trivalent atom, boron in this case, forms a covalent bond with 4 adjacent silicon atoms. So we can see that here. And since 4 electrons are required, a hole, and there's the hole right there, is a hole is formed with each trivalent atom. The number of holes then can be controlled by the amount of trivalent impurity added to the silicon. Since most of the current carriers are holes, silicon doping with trivalent atoms is a p-type semiconductor. Holes can be thought of as positive charges. So all 3 of the boron's atoms, valence electrons, then are used in the covalent bonds, and since 4 electrons are required, a hole is formed for each trivalent. The number of holes then can be controlled by the amount of trivalent impurity added to electrons. Okay, so in the next section here, we're going to start attacking the devices specifically that you will be using in your labs. The first one is, of course, the diode.